One of the main issues with the theory of quantum mechanics is that it seems so counterintuitive. And the reason that's a problem is not because the universe must for some reason behave the way we expect it to, but because our intuition in fact comes from somewhere. Ideally, at least approximately, it's based on years of everyday experience. And so if the theory of quantum mechanics is the correct theory for all matter and interactions, then the classical physics that we experience must somehow emerge from quantum mechanics as it applies to large and complicated objects consisting of many parts. And this is called the correspondence principle. You might recall the Poisson bracket from classical mechanics, which is defined for two functions a and b over the variables in our phase space. And the time derivative of these functions can be given by the Poisson bracket of the function with the Hamiltonian. Note the strong relationship to the Heisenberg equation, which is defined for operators a and b, and the derivative, the time evolution of an operator, is given by the commutator of a and the Hamiltonian. Now in general, we get our information from quantum states by looking at the expectation value of observables, or some moment of observables. And the expectation value, of course, can change over time as the state changes over time. Or at least that's how we look at it in the Schrödinger picture. In the Heisenberg picture, we look at it as the expectation value changing as the operator changes over time. And either of those is right. So we either can group those mentally with the operators or group the time evolution operators with the states. And because we know how these things evolve, we can work out how this whole thing evolves. The easiest way to work out how it evolves is from the Heisenberg picture, however, because we can take this equation here, the Heisenberg equation of motion, and simply take the expectation value of both sides, in which case we get, and that's the equation of motion for the expectation value of any operator A. If we calculated this instead by looking at how the states evolve and then taking the derivative of this expectation value, we would have come to the same equation. So the Heisenberg picture explanation was simply a quick way of getting to that result. Now we can take that result and we can revisit the exercise we did earlier where we calculated how the position and momentum operators changed in the Heisenberg picture. And we can calculate something that's picture independent, which is how the position and momentum expectation value change. So we'll start with a Hamiltonian, and we'll make our Hamiltonian a general Hamiltonian, so we'll have a kinetic energy and an arbitrary potential energy, where this potential is a function of an operator, which remember you can write out as just a power series if we need to. Okay, so let's have a look at that, and we're going to find out how the expectation value of the momentum and the position change. The position doesn't depend explicitly on time, so we can ignore that term. Okay, now again we can take, because the expectation value is linear and the commutator is linear, well then we can do these two terms separately, and we know that the commutator of x and any function of x is going to be 0, and so the only term we have left is the commutator of x and this, and we can take it the factor of 1 on 2m, both out of the commutator and out of the expectation value. And for this term it's exactly the other way around. We get two terms, but the commutator of p and p squared is 0, so we've just got the commutator of p and the potential. And this term over here, remember what we can do is we can write out, this is a product of p and p, so we can take out the p to the left and the p to the right. If we take out the p to the left, we get this. And if we take out the p to the right, we get this. So over here on the momentum side, you'll notice that we have an arbitrary function of the operator rather than just a quadratic function of the operator, so we need something a little bit more sophisticated. And we can use a result more or less straight from our assignment. In our assignment we proved that the commutator of x and p to the n, we can do it for squared here, but we can do it by induction to get an arbitrary n, is just IH bar n p to the n minus 1. And we use that to then go ahead and show that the commutator of x with an arbitrary function of the momentum operator was just basically the derivative. And it's a straightforward reflection of that derivation to show the opposite results. And therefore up here we simply have that, the expectation value. And so we're going to get an IH bar from this commutator here, and two of them, so we're going to cancel that too. And if we divide both sides by IH bar, and same on the other side, then what we've generated is something called Ehrenfest's theorem, which shows us that the expectation values of the position and the momentum behave extremely like our classical variables. In a classical situation, the wave function is extremely narrow, and so the wave packets traveling around for, say, a pen or a chunk of dust is an extremely small, narrow wave packet, and the center of the expectation value is roughly where the entire wave packet is. And similarly with momentum, the center of the momentum wave function is almost single valued. And similarly, the derivative of the potential is going to be a very well-defined value over that wave function. So each of these things become really well defined, and Ehrenfest's theorem, of course, from the correspondence principle must be that those expectation values therefore behave like their classical counterparts. And fortunately they do.